¿Vamos? ¿Sí? Okay.
Los primeros son los que quedamos campeones.
Right, so welcome to session 2. Thanks for coming. Thanks to Ricardo for organizing and so on the seminar. And so today I'm gonna stay in flat space-time, and I'm gonna show you that already in flat space-time you can find surprises if you follow this quantization procedure that I told you about. And in particular, a very pleasant surprise is the Unruh effect. So the Unruh effect is the idea of quantizing a field restricted to one of the Rindler wedges, and I'll explain what that is in a minute. And the Rindler wedge is a region of Minkowski space that you can cover with a coordinate chart, which is called the Rindler patch. And you can regard it as a space-time of its own right. It's a globally hyperbolic space-time, and it possesses a time-like killing vector. So it has a time-like symmetry. It has a symmetry under some time-like translations. So it's got some nice isometry group. And if you perform the quantization that I talked about in the last session, restricted to this wedge with this natural flow of time, you will find a quantum theory. In terms, you'll find a Hilbert space and some operators acting on it. And you can then ask yourself the question of how the Minkowski vacuum looks like in this Hilbert space. It's a heuristic well, of course, you don't know that it's heuristic until you do it. But now we know that it's a heuristic approach in the sense that the Minkowski vacuum doesn't live in this Hilbert space. It's a different Hilbert space, but you can still manipulate it formally and obtain something interesting, and we will do that. And I'll tell you when we get there what that interesting bit is. But so let's get started from there. And then I'll make some, we'll get to some comments on that line having to do with how do we know what the right quantization is. Here we have an example where we're in flat space-time, and we already found two. They define different Hilbert spaces. They have a different Hamiltonian evolution. How do we choose? And what is quantum theory in that sense? How can we say what quantum field theory is in a way that doesn't depend on all these choices, okay? So I'll go back to flat space-time to make those comments, and hopefully I'll convince you that the algebraic approach is a powerful tool for formulating quantum field theory in that sense. Okay, so let me start with a reminder, because I've been suggested by Yuri that perhaps some people would not get everything that I said, and so I want to make sure that we all know what's going on. So quantization in flat space-time is what we did last time, essentially. Well, we did some geometry, but I think that is more or less clear. So we go to Minkowski space, and we have a time translation symmetry generated by some killing vector delta t, which gives you translations in the usual time direction that we have when we describe the metric using these Cartesian-like coordinates. Okay. Tx, okay? So this is a killing vector. It leaves, you can see that it's time-like, and it satisfies the killing equation, which is essentially saying that it preserves the metric. Okay? The form of the metric, it's an isometry. So when you have this time translation symmetry, you can realize the Klein-Gordon equation as an elliptic problem, which is what we did last time, right? So we wanted to solve the following equation to find a Hilbert space and so on. So we wanted to find the solutions to this elliptic equation. And this is how we found those plane wave solutions, if you remember. And we want to realize K as a self-adjoint positive operator in, as we found, L2 n minus 1. We can also view it as an operator in Fourier space by integrating, instead of integrating with respect to the space-time measure, we integrate with respect to the momenta k, okay? And we realize k as a self-adjoint positive operator there, okay? So what that means is that it has real positive spectrum, lambda, which we can, so this is real and positive, and lambda we can write as omega squared, and we find the following relation, which is this this on-shell wave relation that we're all used to from flat standard treatment of the Klein-Gordon equation in Minkowski from quantum field theory, standard courses and so on, textbook, right? Okay, then what we did, well, maybe this is already step 2 to realize this as a positive self-adjoint operator. Okay, then the next step is that we find the solutions using these techniques, and we have a complex structure. We have a complex structure in our space of solutions, and with the complex structure, we can construct a sort of a pre-inner product, let's call it, right? Pre-inner product. It means that it's an inner product, except it's not necessarily positive, okay? So, and how we build it is by using the complex structure of the complexified solutions that we have, right? So we are interested in complex solutions and write it in this way, right? So where this bar, complex conjugation, okay? Then we realize that this pre-inner product is actually an inner product if we restrict to the space of positive frequency. So then we go to the space of positive frequency, which, if you remember, is it satisfies the follow relation for the modes, okay? And on this space, this friend of ours is an inner product, okay? And this is called a pre-Hilbert space. And this is a pre-Hilbert space of our quantum theory. And almost everything is done except that. For it to be a Hilbert space, there's a technical condition saying that it has to be a complete vector space, and that is tantamount to adding some limiting points of Cauchy sequences. There's a standard procedure for doing this in mathematical literature, and it really isn't the point of this course to go into those details. But when you do that, you find the Hilbert space of the theory. Okay? And so just for recap, we find a Hilbert space which is L2 Rn with an inner product L2Rn. Let's use dnk as a measure, and it has an inner product given by minus I. Okay, which we're going to call the inner product, right? Okay. So that's our Hilbert space, and we can represent the field, the quantum field, in the following way in terms of some annihilation and creation operators, 2 pi and to the minus 1 omega. So I'm just doing a recap, okay, guys? I think it'll be good for you to remember what we talked about, because today we're going to do the same in the Rindler wedge. Okay, plus conjugate. Okay, plus conjugate. Okay. Right, plus, by conjugate I mean star, right? And star on operators and complex conjugation on functions, okay? And so we represent the quantum field in this way, and it satisfies the commutation relations. Okay, for V and W in the Hilbert space, right? Which is also, and it also satisfies the other two relations which are simpler, namely that creation operators commute amongst themselves and annihilation operators as well. Okay? So that's the quantum algebra of the Klein-Gordon field in this system. And these annihilation and creation operators act on the Hilbert space to construct the Fock space. So in particular, when I act with a creation operator, I get a vector. Here, when I act on this vector, and I'll tell you what it is in a minute, it is the vacuum state of the theory. Okay? It's just defined in this way. This is a definition. Okay? So now the Fock space is constructed by taking symmetric. So because this is a bosonic theory, we take the sum from n0 to infinity of H. And by circle, I mean, okay, by circle I mean symmetrized tensor product, right? So it means that A tensor B, or A tensor symmetrized B is the same as B tensor symmetrized A, okay? That's all I mean by this circle notation, which I think I didn't introduce before. And so for the purposes, so of course you can always go between, as you know in quantum mechanics, a Schrödinger and a Heisenberg picture. And this time around I want to really focus on the Schrödinger picture, because in the Heisenberg picture, because it'll make the discussion for the Rindler space and quantization on Rindler clearer. So I want to consider that these vectors are always on a fixed slice of time 0. These are restrictions of solutions to time 0. Whereas the field will evolve in terms of these operators, which this is simply the restriction of that to time equals 0 surface. So let me tell you what that is. Okay, and pi is phi dot. By dot I mean the derivative with respect to t, right? Of tx evaluated at t equals 0. That's the momentum. And these two operators will evolve with the Hamiltonian evolution of the theory, with the quantum Hamiltonian, while the vectors will remain fixed. This is taking the Heisenberg point of view, okay? Of course, they evolve in a way that is consistent with saying that if I restrict the solution to, say, t equals 3, then if I evolve this to t equals 3 and restrict, this is what I should get, right? Okay, and I was supposed to tell you how the annihilation and creation operators act on the Fock space, and I got all my constants and factors wrong because I didn't remember how they went. So I went and checked. And if I suppose I have a vector which is in the Fock space, and let me call it like so, such that, of course, this is a complex number, this is a vector in the one-particle Hilbert space, and W2 will be a vector here, and so on. And typically, a Wm will look like this. If you expand it in, it's going to have some coefficient here. Okay. And it's going to have a basis, of course. Okay, I'm calling this circle, dot, 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 circle, AKN. And notice in this representation, remember this is the symmetrized tensor product. In this representation, you get your textbook creation annihilation operators with momentum k that you're all familiar with, right? If you've done, for those of you who have you all done quantum field theory courses, the first one or something like that? Yep. No. Okay. Well, in a textbook course, what they say is, here's a field and it's classical, and now we quantize it, and it looks now like this, AK plus field AK dagger bar integral, and this is now a quantum field, and it acts on a Hilbert space like this. Omega is a vector with momentum k, right? And this is the same thing, except we are treating vectors in an appropriate way where they're suitably smeared and so on. Okay, but don't want to talk about that. But this is your creation annihilation operators that people are familiar with in standard quantum field theory treatments that are less precise. And I told you I was going to tell you how they act on these vectors in Fock space. So the annihilation operators acts in the following way. It will contract with, so where's my W? Where have I written it? So the annihilation operator will completely make the complex number disappear. This drops off from the expression, and then it contracts with the one particle Hilbert space vector, and then it will contract with the next one, but with a factor of square root of 2. Okay? And then it'll contract with the next one with a factor of square root of 3, and so on and so forth. So you always have so the 2 is going to come here, and if you will, there's going to be an MVWM here, ... Okay? That's how it acts, the annihilation operator. The creation operator acts in a very simple way as well, right? By the way, this is all conventions. You might find people that define the creation operator or the annihilation operator with a square root or a factor or whatever, and then this will not appear in this expression, but it'll appear somewhere else, and so on. Okay? This is just conventions. This is the convention of Wald in the appendix of Wald's little red book. Okay? So this guy just comes in and tensors. You put a 0 slot in the complex number entry, and then it symmetrizes tensor himself with that complex number, which is just itself times the complex number. And then it goes and does the same with this guy. And now there's a square root of 2 factor, which let me write it here. Square root of 2v. And there's the square root of 3v w2 ... And there might be a square root of m plus 1 v wn. And so this is the sort of factors that appear when you do quantum mechanics and you do the harmonic oscillator. Do you remember the harmonic oscillator in this representation where you have creation and annihilation operators, right? In quantum mechanics, it's the same story. So people like to think of the Klein-Gordon equation as a harmonic oscillator on each point of space-time. They like to think of a Klein-Gordon field in this way, and it's quite a nice way to think about it, to be honest. It's, of course, not, there's no mathematical theorem that tells you this is exactly what it is, but it's an excellent pictorial notion. Okay? And of course, I have to tell you what these contractions between these complicated products of symmetrized tensor products of creation operator. You see, this WM has a complicated structure. It's the symmetrized tensor product of many of these creation operators acting on the vacuum. So how the hell do you contract this with V? Well, you simply use the algebraic relation that tells you that the contraction is a commutator, right? And so contracting that is simply T and K. So I'm going to write V as integral dk dk. Where are you? AK acting on the vacuum. Okay, so I'm going to write V like that. W has that form. And then, of course, you know what this contraction is going to be now, because you know what the commutator does. It's a bracket. So in particular, it has nice algebraic properties, and you can take the bracket of a product in the ways that you know. So here, I take the bracket, AK hat, AK 1 hat, AK M. Why am I confused? Ah, yes, of course. This goes like that, but now it acts like that. Vacuum. And you know that if you take the Lie bracket of something with the product of something else, you can distribute it in nice ways.
I guess you're missing a bra vacuum.
Where am I
from the
missing?
B, no? There should be one from the B and one from the W.
In the right side of the equation.
Actually, I think your commutator would be proportional to. Ah, no, it's not. Okay. So yeah, you're missing something, no? Because your right hand side is a.
Oh, sorry. Yeah, you're right. I want to.
Right, your left hand side is a complex number there, and your right hand side is a head. So.
Yes, I want to call this a. This is still a vector because you're contracting only one thing against.
Okay.
You see, I have a bunch of creation operators acting on the vacuum and just one annihilation operator there, so it's fine. Okay. This is still a vector. So this is gonna give you 1 degree less of. If this is an m particle state. By acting, you see, when I distribute this, what am I going to get from here? So, for example, well, you see what I mean, right? So you see, formally, let me just focus on this bit. Well, it's all symmetric, so I'm just going to write it like that, okay? And this is what? Well, it means I use my Dirac orthonormality that you remember to get delta functions, okay? And I get delta k minus ki, and I get a k dot dot dot, no, a k1 dot 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 a k I minus 1, a k I plus 1. Dot 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 a k m, right? Stars, 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 stars. Okay. And this is going, and this is. So I'm gonna do this for every value of.
Okay.
Yeah, from I equals 1 to m, right? So for every, it's gonna hit every k like that. Then this delta goes inside that integral and it kills one of the integrals. And you can continue, you can express this in as much detail as you want using these relations. And you see how to contract one of these vectors with an n particle vector. Okay, did everybody get the idea of that? Yeah?
So what does the bracket with B, the bracket of B and WM means?
The bracket.
What does that mean? Yeah, the left hand side of the equation.
Yeah, the left hand side of this.
Yeah, you said it wasn't a complex number, so
No.
it was still a vector.
Yeah, it is a vector. So let me think of it in this way. This guy will act as a dual vector, and it will take Wm, which lives in. Let me write it more precisely. It will go from. So I'm now thinking of a pure m particle state. So this is m symmetric tensor products. Okay. All right. That's the right notation. Let me do that. It's an m. I take H and I symmetrize tensor product it m times. Okay, and it'll go to where? It'll go to m minus 1, like that. Okay, and it'll take a vector here Wm, and it'll send it to V Wm. But you see, I'm only entering with one covector. It's like when you have you remember from GR, for example, if I do a contraction of a form with a, I don't know, 3 tensor, right? Right? So then I write that like TA, TAB, C, and this is a 2 tensor. And the idea here is the same. It's exactly the same idea, right?
Yeah, the notation is a bit misleading. But
the notation might be a little bit bad. But the nice thing about this notation is that you can write everything explicitly in terms of these annihilation operators and so on, K, sort of sharp annihilation and creation operators that people like from standard textbook quantum field theory courses. But that's the idea, okay? So this is what we have done last time with a little bit of added stuff, namely that Fock space discussion that we didn't do in much detail last time. And now, as I said, I was going to stay in the Heisenberg picture. I want to tell you what the Hamiltonian of the theory is and what it does, right? Of course. So, remember we have these operators, let me call them 0, x and pi 0, x, which are the 3 momentum and 3 field, okay? And I can evolve them using the Hamiltonian, which you can obtain by using, you write the functional form of the Hamiltonian in terms of momentum and field in the standard classical field theory way. Then you replace those guys by these operators, and you get the Hamiltonian.
so sorry, you have one Cauchy surface.
You have one Cauchy surface.
You call that T equals 0.
That's T equals 0. Yes.
And then you extend the foliation on all space-time.
Yeah, that's right. And I'm going to tell you what the fields look on every foliation by acting with unitary coming from the Hamiltonian. Okay? And so this is the standard alerta sísmica. What? Not sure.
I guess we're all too
Okay, so
in any case, if it sounds, our place to go is the roof.
yes. So anyway, this is a Hamiltonian. You have to renormalize it because it's an operator that is quadratic in these fields, but I will not get into that at the moment. We'll have plenty of time to look at renormalization later. But this is the Hamiltonian, and the evolution, say, of one of these operators. Say, if I want to, if I initially define it on a slice here, which is t equals 0, and I define my field phi 0x, and I want to evolve it to phi tx on a slice t equals, let's say, tf, then I use the following formula. And I use the commutator to get an expression for this. It's a convoluted expression, but it's just to give you an idea of what the Hamiltonian operator does. Okay? Okay, so that's it. So end of story. We have our construction in the Heisenberg picture for the quantization of the Klein-Gordon field in Minkowski space. We have a Hilbert space that we associate to a slice. And we have operators that evolve in time with this Hamiltonian, which is given in terms of these creation annihilation operators. Okay? This is a renormalized expression because it's quadratic in the fields, but I haven't shown you how to renormalize and all that because we will do that later. For now, just imagine that you wildly replace the quantum expressions for the classical Hamiltonian, and you find an infinity and you remove it. Okay. Normal ordering, exactly. And so that's everything we need to do for the moment. And of course, the Hamiltonian is very much tied to time evolution, as you can see from that time evolution expression. And the notion of, and of course, how you write the Hamiltonian, how it depends on those creation annihilation operators, depends on the whole Hilbert space construction, which in turn depends, as you will see, on the choice of time. So now let me talk to you about Rindler space. I wonder, last time we went all in a row, and I was told by my girlfriend this is very non-pedagogical. So maybe we should take a break in like 10 minutes or so. Right? Do you guys feel like taking a break in 10 minutes, or you're like Landau school kind of guys?
Maybe
You're
less time.
asking the wrong question, right? We always start in the mood for a break.
Maybe less time for break.
I mean,
10 minutes would be.
no, we take a 5-minute break in 10 minutes.
Okay.
In 10 minutes, we take a 5-minute break, okay? So this is Minkowski space. And I've drawn some x's there, which you might be wondering what they are. So this is Minkowski space. This is the t-coordinate, this is the x-coordinate, and this is Rn, okay? In 2 dimensions. And as you know, as you all know, whether you come from a high energy background or whether you come from a gravity background, Minkowski has a lot of symmetry. In fact, it's a maximally symmetric solution, okay, of the Einstein equations. And one of the symmetries that it has is a boost symmetry, right? So let me, well, I have written it somewhere, but I can also perhaps try to write it by memory. But the boost looks, I think this goes in that direction, this goes in that direction, and this goes in that direction. And so it's a vector field that takes this form, and in each quadrant it takes a different form. So in this quadrant it's a time-like vector, future pointing. Here it's a space-like vector. In this past region it's a space-like vector, and here it's a time-like vector pointing to the past. Okay? And how... Sorry?
The opposite direction in the lower one?
It is the opposite direction in the lower one. That is correct. It is the opposite direction in the lower one. And let me write it, which I have it somewhere here. Okay, well, it looks something like x dt plus t dx. And let me verify that, just that I don't have a sign that is wrong. Yes, I got it correct. Okay. Okay. So this is how the vector field that generates boosts look like. So if you will, in abstract index notation, you would put a little index there. Okay. And you can see that it defines something called a killing horizon. So when you have in fact, it's called a bifurcate killing horizon because it bifurcates around this point. And so you can, so what is a bifurcate killing horizon? When you have a killing vector that changes character, so here it's time-like, but here it's space-like, and so on. In between, it has to go to something else, and it becomes null. So where these killing vectors become null is called a killing horizon, okay? And Minkowski has a bifurcate killing horizon. In fact, it has many depending on where you put the origin of your coordinates, of course. And, but in this particular set, it appears very clearly here. And it divides Minkowski space into several regions, right? So I want to restrict myself to this region. And this region is called the right Rindler wedge. This is the right Rindler wedge.
What's the wrong wedge?
The wrong wedge is the left one, unfortunately. This is the left Rindler wedge, and these are things that Well, they have no names. This is the Einstein universe or something. When, I think so, right? Milne universe. That's the Milne universe. Thank you very much. So how do I view this? Let me view this as a spacetime of its own right. What does it have? Well, it has a Cauchy surface. In particular, this t equals 0 surface restricted to this wedge is a Cauchy surface. It is a Cauchy surface of the whole spacetime, and it is a Cauchy surface in Rendler. Okay. So if I want to draw a conformal diagram, let's say in 2 dimensions, this is the bifurcate killing horizon, and this is the right Rendler wedge. This is the left. This is future Milne, and this is past Milne. Okay. And we are here, and you can see that this is a Cauchy surface of Minkowski, and it's also a Cauchy surface of the Rendler wedge, if I forget about those 3 other pieces and view this as a spacetime of its own right. Okay. Very good. So we have a globally hyperbolic spacetime, which is Rendler spacetime. Okay. And I want to consider it in 2 dimensions. I'll make a construction in 2 dimensions because it doesn't need to be more complicated than that to see a few points. Okay? So I want to write the Minkowski metric in a new set of coordinates in this form. Well, this is the metric, right? So let me call that AB. AB. Okay. This is a coordinate, and I'll tell you what it is in a minute. Eta is a coordinate running from -infinity to infinity, and Z is a coordinate running from 0 to infinity, and they're related to the usual Minkowski coordinates in the following way. Okay? And so this is the same Minkowski flat metric written in a different set of coordinates. Okay? And it is a set of coordinates that covers the right wedge in a particularly nice way. So let me draw the right wedge here. Okay? And so eta constant surfaces run like that. Whereas Z constant surfaces run like this. Okay, so that's the. So these are curves that are indeed these nice boosts that we were discussing. Okay, and you can in fact verify that the boost killing vector that I've just written takes a very simple form in these coordinates. Like that. Okay? So this d eta is the boost generator. And curves that follow the coordinate eta running are integral curves of the boost. Okay? So curves parameterized by eta from -infinity to infinity are integral curves of the boost. Okay? It is also interesting that this parameter A appears here. And that parameter A is associated with the acceleration of these curves. So if you would have an observer running along these curves, they're not geodesics of Minkowski space, and they have an acceleration, and when you calculate that acceleration is that parameter A. Okay? So that's why it's called A from acceleration, typically. So I'm going to do now, I'm going to do the quantization in this wedge using these coordinates. Okay? So let me, so I'm on page 3 of my notes, and I have many. So I'll go very quickly with this. I thought I would give you many details, but I won't. In fact, I will go rather quick, because I think we'll take a break in 5 minutes, and then I'll... But let me just get started with the idea. The idea is that we want to construct a theory. We want to construct it on this slice, the eta equals 0 slice. Okay? We want to take this as our initial surface. We want to construct a Hilbert space here, and operators on this surface. And we want to construct a Hamiltonian that makes these operators evolve. Okay? But since my notion of time, notice that this killing vector here is the most natural notion of time in this wedge. I'm gonna construct a Hamiltonian for the theory that evolves with respect to this notion of time. We're gonna see that it's different to the Minkowskian Hamiltonian, and we'll see that the whole construction is quite different, right? And in particular, we're gonna construct a theory that's unitarily inequivalent. That's the jargon for saying that they're different theories. It means that you cannot map vectors in one Hilbert space to another by a unitary transformation. And it means that you cannot map operators to operators on the other Hilbert space also acting adjointly with a unitary transformation, right? So we're not just doing a unitary transformation, we'll construct a different theory from scratch. And you'll see in a sense what the punchline of that is, right? So here naively we think we just change coordinates, we should get the same thing, but we don't, okay? So that's a bit of a punchline in advance. So maybe it's a good time to break now. Let's reconvene in 5 minutes, okay? Ah, yeah, because I had a cat on the right, that might have been confusing, right? Yeah, I mean, you put a cat if you want, and it's not important. It's just a piece of an inner product.
Okay. You can write the cat with the you have in that case to put all the functions inside.
Yes, yes. Okay, so I'm going to gloss over the quantization very quickly because it's just what we've done before, right? So you start with a wave equation. You write the box operator in terms of these coordinates, and it doesn't look like the old box operator anymore. However, it's still a static problem, so you can still use the same techniques. You can decompose it into a time-evolving mode with this parameter j squared, which is going to be a spectral parameter in the solution of the elliptic problem, and the time eta, that is the natural flow of time in this wedge, right? And then you try to find these eigenfunctions of the operator k, which are z solutions, z modes, right? Constant time modes. So the elliptic problem looks like this in these coordinates, and it's a positive self-adjoint operator on L2 R plus, because z runs from 0 to infinity, so you only integrate in R plus. And it has a measure that is taking into account the fact that the metric looks a bit curved. I mean, it looks as if it were curved, but it's not really curved. So this is a suitable measure that renders this into a self-adjoint operator on that Hilbert space. Okay. The solutions to the problem then you obtain from this eigenvalue equation, and they are these mode solutions psi j of z, and they are given in terms of these sine hyperbolic functions and these kij's, right? And so a kn is called a modified Bessel function of second type of order n. So this is of imaginary order j, right? This is just a special function. It's very well known in the literature and so on, and that is just the solution that you get by solving this problem, right? So these are the modes that satisfy this eigenvalue equation.
Is P sub index j, or the product of 3.14 times j?
Where?
In the argument of the hyperbolic sign,
By j.
the product of
Pi times.
Pi times j. Pi times j, right? Okay. M times z. Okay.
J is not an integer, is it?
No, j is a continuous parameter. It has positive real spectrum, so j runs from 0 to infinity, right? Okay. And what is the then we can quantize in the way that we know. We know how to do everything, right? We know that we have a symplectic structure, we can construct an inner product, we can do everything that we have done before, and we can quantize this in the following way. Okay, so we have our annihilation operators and we conjugate to get the creation operators.
You still have the problem of the negative modes here?
Yes, you have positive. You have these positive frequency modes and you have some negative frequency modes. And in order to get a Hilbert space, we'll keep only the positive frequency modes. That's a selection that we're going to do, right? A choice. Okay, let me tell you a few more things about these modes before we go any further, because they're good for calculations. So they are Dirac orthonormal in the sense that we learned that the plane waves were Dirac orthonormal. What? Kz delta j minus k. So that's Dirac orthonormality. And they also provide a resolution of the identity, which is in fact a trivial relation when you have plane waves, but it's not trivial when you have these modes. This resolution of the identity that I'm writing here is related to the fact that there exists no bound states on the theory. In other words, the eigenvalue problem solves everything that we have. Every single solution can be written, can be expanded in terms of these eigenmodes. There are no funny solutions hiding in the negative spectrum or anything like that, which are known as, everything is there, okay? Okay. Now one more little thing that we should say. We can construct our equal time operators from this solution. We can write our operators which are equal to phi 0 x and equal to equal to d eta, sorry, this is z, it's not x, this is z, and this is z. Z at eta equals 0, right? So that's field and associated momentum right? And we have our CCR algebra, which says that for any V and W in the Hilbert space, and the Hilbert space, of course, is taking these modes and constructing the inner product in the usual sense, right? Okay. In the one particle Hilbert space of the theory, we have that AV, A star, W equals where are we? PW, space times the identity. And similarly, AA, A star equals 0. Okay, suitably taking vectors, right? So the CCR looks exactly in this, it has the same form as in Minkowski space, right? Despite the fact that we've done quite a different construction, the algebra of commutation relations is the same. Finally, we have a Hamiltonian for the theory, which is equal to the integral of dj, which is our spectral parameter, j, A star J, A, J. That's the Hamiltonian of the theory. And our field operators evolve with the Hamiltonian defined in this way. Okay. I'm happy that I've managed to go quite quickly, but this is something that we have done before. Okay, now I want to point out to some geometric remark. I want you to notice that the eta equals 0 surface is the same as a t equals 0 surface in the whole Minkowski space, right? Moreover, eta is normal to this surface at this point, of course, and so d eta is normal to this surface at this point. And in particular, based on these geometric observations, the restriction of the whole field of the, let me call it like this. Okay? The restriction of these fields that we obtained before to here, to this surface, on this surface at time 0, should coincide with the ones that we obtained from this description. They coincide because this on this eta equals 0 surface, I can describe it saying it runs from x equals 0 to infinity, and it has vectors that are orthogonal to it by dt, or I can say it runs from z equals 0 to infinity and it has normal vectors that are d eta. So the description is on this surface is the same. Okay. So now let me do something else. Let me write the field in terms of Minkowski coordinates. And let me write the field in terms of these Minkowski creation annihilation operators, and let me write it in terms of these new ones, right? And this will give us a relationship between these creation annihilation operators and the ones that we had in Minkowski space, okay? So the first thing that I want to do is I want to take this expression, and from it I want to get these two guys, phi and p, as operators on a slice, and I want to invert the relation in order to obtain the annihilation operators in terms of them too, okay? So I can do that. I can do that using these nice, right? These nice relations, these nice orthonormality relations that I have here, and this whole delta resolution. They allow me to invert very easily phi and p hat to get A and A star, okay? In particular, using them, I get that AJ is equal to 1 over square root of 2 times square root of j integral from 0 to infinity dz over z plus I over square root of j integral from 0 to infinity. Okay, that's how the annihilation operator looks in terms of these two, field and momentum. Now I'm going to replace them with the ones that I had in Minkowski, that I can calculate using the plane wave modes and so on, in terms of the creation annihilation operators that we obtained on Wednesday. Okay? And I'm going to replace those expressions. Do you want me to remind you what they look like? Maybe I'll remind you what the field looks like at least. So in Minkowski, we said, now I'm in 2 dimensions. So I've restricted it to n equals 2. And I'm calling the Minkowski creation annihilation operators B, just to distinguish them from these ones that I'm calling A now. Okay? And there's a similar expression for Px, right? And what I get from this is that I can express the Aj in terms of the Bk and the Bk star. And I get the following expression. Well, there's a few integrations that have to be done, but I'll try to go quickly, and there are standard integral expressions for Bessel functions, which, remember, our k is the Bessel function, and what we get is the following. So what is relevant about this complicated expression? Well, what is relevant is the appearance of both of these operators in Minkowski space. These are two operators in the Minkowski vacuum, right? This is a formal relation because this now looks like an operator in the Hilbert space of the previous construction, but it's an operator in our Hilbert space. And the relation is formal, there are subtleties. Okay? But what is relevant is that if we had only this contribution, then we could imagine that we could find a unitary transformation from one to the other. We're just simply writing one of these annihilation operators as a linear combination of the other one, right? We write the annihilation operator in this theory as a linear combination of annihilation operators in the other theory. And by complex conjugation, the same goes for the creation operator. So they're all related by a linear transformation, and this linear transformation would yield you a unitary transformation that can allow you to go from one to the other. However, the appearance of this other guy is an obstruction to doing that. So this is no longer the case. And in particular, the two theories are not unitarily equivalent. By the way, this exercise of writing one set of creation annihilation operators in terms of the others is called a Bogoliubov transformation. It's very useful in quantum field theory in curved spacetime, and in particular is, for example, something that you can use to see cosmological particle creation in a more sophisticated scenario, but the idea is exactly the same.
But you will need some geometrical coincidences like the ones you pointed out, no?
Yes. In particular, what you need is something to be an asymptotic. You have two notions of time, and they're both asymptotic killing vectors, and then you can find ways to relate them. You need asymptotic killing vectors always to define these Bogoliubov transformations between so-called in and out vacua and so on. But the idea is the same, okay?
Is this a general form of the of that transformation?
Yeah, the general form. Yeah, the general form is I get this mode in terms of this and this with a coefficient.
Okay.
Yeah, that's the general form.
That's omega ij.
What's omega ij? Where is it?
The square brackets with an ij.
It's just to the power I imaginary unit j.
Okay.
Okay. Now, let me do an interesting calculation for you with this. With this expression. So what is an interesting observable in our theory? Well, an interesting observable is the Hamiltonian. And particularly, it tells us the energy. It tells us the spectrum of the system, the particle content, how much energy is put in the system, right? So let's calculate the expectation value of our Hamiltonian. But let's calculate using this expression in the Minkowski vacuum, right? Let's imagine that the Minkowski vacuum lives in our Hilbert space, right? And do the following. Integral dj 0 to infinity j aj star. So if we use the vacuum of our theory, which let's not call it M, if we use the vacuum of our theory, this is 0 because it's just annihilation operators acting on the vacuum give you 0. But let's think of the Minkowski vacuum. How does the Minkowski vacuum look in our theory? Okay? And you can do a bunch of algebra using this Dirac orthonormality and delta resolutions, and it's just a very straightforward calculation. And what you get is the following. 1 over 2 pi, a factor here, and then something else. This is an exercise because I've done it like 5 minutes before we came, and so it might have minus signs, blah, 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 and so on. But you can check it. It's a very simple calculation. And so 2 comments are in place. First of all, this number is infinity. You can see that this goes to infinity as 1 over k. So the behavior of the integrand at infinity is 1 over k. So the integral at infinity goes like log k, which goes like logarithm of infinity. So it has a logarithmic divergence, right? This is it's indicative of the fact that this vacuum doesn't really exist in in our Hilbert space. But what is more relevant is the second term, right? The second term is more relevant. It is a Planckian spectrum from statistical mechanics, right? It's a black body spectrum. Well, it's the spectrum that you would get for bosons. For fermions, you would get something like that, right? It's a Bose spectrum, Planckian spectrum, right? And what it indicates is that in a sense the Minkowski vacuum looks like a bunch of particles with energy J. It looks like a bunch of particles of energy J as a heat bath. This is a thermal spectrum. So the Minkowski vacuum, from the point of view of these observers that move naturally along these curves, looks like a thermal state, right? And what is the temperature of that thermal state? Well, throughout the construction, we've chosen our time flow to have unit acceleration. Throughout the calculation, I've set implicitly a equals to 1. But I can restore it because I simply do it by dimensional analysis. And yeah, and I can restore it like this. And now the temperature is proportional to the acceleration that I have when I move in this space-time.
Inversely proportional, isn't it?
Is it inversely proportional? Let me check.
No.
The temperature cannot be inversely.
No, it's proportional.
I have it in my notes.
Because the expression in the distribution is e to the
Yes.
energy, beta energy.
Yes, you're right.
Energy over
Yes,
T.
you're absolutely right. It is. It is inversely proportional.
Okay.
Yeah. So for an observer that flows along these lines and describes the universe only in this Rindler wedge, the universe in the vacuum of Minkowski space looks like a thermal state at temperature proportional to acceleration. And this comes from a more general result, which has to do with the geometry of this space-time, right? So in a sense, what we have done is we've taken Minkowski space and we've forgotten that half of the data that one would need to obtain all the information of Minkowski space, half of it has disappeared, right? This is what we have done in this construction. And the fact that all the modes that propagate on this wedge we are ignoring. The fact of ignoring this is like taking a partial trace on this side. It is exactly taking a partial trace on this side. And getting a state after partial tracing which is thermal and which has a temperature in the sense that we have obtained here. Exactly that temperature. I mean, here we've restored the acceleration because we want to give it more a physical meaning. but you would get a temperature of 1 over 2 pi. And this is a geometric statement about how we've done this construction and how we have forgotten about half of the quantum modes that live in Minkowski space. Right? So remember that the vacuum is a highly entangled state. So when you trace out half of the modes of the vacuum, you're losing a lot of information, right? Okay. I have about half an hour, so I wanted to talk to you about particle detectors, but maybe I'll skip that and talk about that when I see black holes. So there is a natural way. So here we've made a whole construction. We've constructed another Hilbert space. We've given it some geometrical meaning, and we have a lot of symmetry, and we know what to do. But what would happen in general for an observer? Again, going back to Minkowski space, we're in Minkowski space here. And we have now described the universe using this quantization from the point of view of a uniformly accelerated observer that follows the orbit of a boost, generated by a boost. But how would an observer that moves like this see the Minkowski vacuum? Well, or one that moves like that. Then it's not so simple to come and write a vacuum that is well adapted to this curve and so on. And there is a concept that is called particle detector. You basically couple the field. You take the Minkowski vacuum, you do the construction in the Minkowski vacuum, you couple the field to some probe, which is quantum mechanical, typically with 2 degrees of freedom. And then you look at the transition probabilities in this guy. And you can read off how he perceives the vacuum in how he gets excited, right? So if it moves on a static trajectory, it'll just occasionally have some spontaneous emission, but that's it. But when it moves to doing something funny, it may absorb modes, it may release them and do more interesting stuff. I wanted to do this now to clarify the meaning of this construction, but I think now I'll just say it in words. This guy is moving on an accelerated orbit in Minkowski space. For him, the universe looks like the Rindler wedge. He's ignoring the rest of the modes that go on the other side of the space-time, and this causes him to see the vacuum state as a state at a temperature T, right? The Minkowski vacuum looks to him as a state at temperature T, okay? That's the meaning that we can give to that construction. But when we look at particle detectors, it'll be very clear. And I'll do it in the context of black holes. Okay, so we will see them, but maybe for today I'll try to go back to point D, which is, let's go back to flat space-time. Let's compare these two vacua, these things that we have done, right? Okay, so in a sense, the Klein-Gordon field, the classical Klein-Gordon field, is a covariant object. And one should be able to describe it in whatever coordinates one wants to do it, right? It's defined by some equation of motion that is independent. I don't define the Klein-Gordon field like this. I simply don't. That's not how I define the Klein-Gordon field. I define it like this. And what we have done now is we've solved it in two different coordinate systems, and in a sense we've gotten equivalent quantizations, right? But the point is that in doing so, in doing this whole construction, we have committed an unspoken sin in some sense. We have singled out a time, we have given a special character to a time, which in the case of construction from Wednesday was the time generated by this killing vector of Minkowski space. And today we gave a privileged role to the time generated on the right Rindler wedge, where it really is a time, by this vector. We have singled out we have given a special role to two of these isometries of Minkowski space, which are not the same, they're different, but they play a special role in our construction. It's not just the fact that we have splitted the solutions into positive and negative frequency modes with respect to this guy or with respect to this guy, but we have then gone on and cut it to half and kept only the positive frequency modes for describing the Hilbert space. So in doing so, of course, when taking this guy, we've constructed a one particle Hilbert space of Minkowski, and when taking positive frequency modes with respect to these guys, we have constructed a different Hilbert space. In particular, let me tell you something that I haven't told you. This is, of course, called the Minkowski vacuum, as you know. This one is called the Fulling Rindler vacuum. Okay, that's the name of this vacuum. So you see that by choosing positive frequency or negative frequency with respect to this or this with respect to that, we've sort of given a special character to these notions of time. But then we've gone on and really kept only positive frequency and forgotten about all the other solutions. And that's really and that is necessary to construct the inner product of the Hilbert space. That's a crucial step from going to from this symplectic structure to the inner product of the Hilbert space. So it is a necessary step to do this construction, but it is highly non-covariant. It depends completely on how I choose time. So states are in this sense non-covariant objects. However, on the other hand, when we've done our construction in Minkowski space, we have obtained, well, in Rindler or in Minkowski, we have obtained these commutation relations. And we have also the other two. Okay, I'm not going to write them. Plus AA star. Okay, plus those other two. Okay. We have obtained these commutation relations. And when we have done it, when we have done it for say Rindler, and when we have done it for Minkowski, in the Minkowski vacuum, in the construction of the Minkowski vacuum, these are now vectors in Minkowski space, of course, so let me just capitalize them to distinguish them. We have this is in Rindler, this is in Minkowski, plus the other two. Okay? We have obtained the exact same form of the algebra. So the algebra of observables, which satisfies these commutation relations, doesn't care what construction you do, what time you choose. It always becomes a construction of this form. It always has this form. It always satisfies the commutation relations that define a bosonic field. So the algebra is fundamental. It doesn't care, you know, in some sense. It doesn't care whether these vectors are vectors that belong to the Fock space that we constructed out of a Rindler vacuum, or it doesn't care if these vectors are the Minkowskian ones. It doesn't care where these vectors live. The form is the same, okay? And I could construct some other crazy vacuum and I should get the same form if I'm describing a Klein-Gordon field, right? So the algebra is a fundamental defining property of quantum theory. So what is then the vacuum what about the states? What role do they play? Well, states, we can view them as objects to take expectation values, right? So let me say I have an operator on a Hilbert space. Okay. Let me say I have an operator on a Hilbert space. That's just notation for saying that this is a linear operator on a Hilbert space, H. Okay? And what is quantum theory about? Not just quantum field theory, but quantum theory in general. We have some observable, which is an operator on a Hilbert space. We have states, which are vectors on a Hilbert space. And the Hilbert space has some inner product structure. Let's say W and V, which we can use to compute these kind of things, right? And this is a complex number. And these are measurements in some gadget, in some dial that we perform in a laboratory, okay? So we have operators, we have states in a Hilbert space, and we get a complex number out of taking expectation values. How do we think of this in a perhaps more in a slightly more abstract way? Well, the operators have to satisfy some special relations, which are these commutation relations. Particularly, they have to satisfy some algebraic relations. So we can think of operators living in an operator algebra. An operator algebra is simply an algebra of operators on a Hilbert space. And let me call that A. Okay? What does it mean? It means that the operator, that the observable, is an operator on a Hilbert space, and it also has some algebraic relation. Okay? So this is an observable in an operator algebra. Okay. And now I want to think of states. I want to think of a state. So what is an operator in the vacuum state, for example? Well, an operator in the vacuum state is that. Okay, what's in some other state? What is the expectation value of this operator in another state? Well, it's that, and this is whatever you want it to be. This is 3 and this is 2i. Some complex number, right? Okay. So I can view a state, I can view the state psi, or I can view the state omega as a map. I can view it as a map. So I can think of omega defining a map. What map? The map okay, which takes O and gives me some, well, which goes from this algebra of observables to C and takes O and gives me that in C. Okay. But of course, if I tell you how the vacuum acts in O, it doesn't really tell me much. It just tells me a little bit of information. But if I tell you how this map acts on every single observable that I have defined on my theory, then I know basically everything about it, because I know what the expectation value of every observable is. in this state. I know every expectation value for every observable in this state. And this is everything that I can get out, say, in a lab out of this state. This is how somebody in a laboratory would tell me, it's in the ground state. Because they would measure a bunch of observables and they would get the energy is 0 and so on and so forth. Well, hopefully they would get that if they're good experimentalists. And they would tell me, it's the vacuum state. Or they would get something else and they would know by the things that they wrote on their computer and they plotted in Mathematica, it's this state or something like that, right? So the idea and the direction in which I want to go is in thinking of observables as belonging to some algebra and thinking of states as maps from that algebra to the complex numbers. That's the point of view that I want to take from now on, that I will explain in more detail next time. So this is just some motivation coming from flat spacetime that we're already, without introducing any curvature, we've spent half of the course without introducing any curvature. And we already see that. In a sense, the Hilbert space is... Both the Hilbert space and the observables are important, but some are more important than others. They're both equally important, but some are more equal. Some are more important. Well, that's from Animal Farm. It's about reference. But that's the idea. That's the direction in which I want to go. And then the next level of abstraction will be not to think of the operator, not to think of observables as element of an operator algebra, and these defining maps as living in a Hilbert space, being vectors, being cooked out of vectors in a Hilbert space. But I will further abstract the notion and think that observables are just algebra elements. They are just living in an algebra that satisfies something. For example, they satisfy, for example, this. Okay? There's no reference to any Hilbert space or anything. They satisfy a relation like this. And that's an algebraic relation defining the algebra of observables. And then states are simply maps from the algebra of observables to complex numbers. And then I will show you that there's a procedure coming from this abstract point of view to represent these abstract algebra elements as operators on a Hilbert space and the maps as expectation values on a Hilbert space. That'll be for next week. And the beauty of that point of view is that it doesn't care about what the curvature of your space-time is, what your time is, what blah, blah, blah. It's quite general. And then you go on, you push the construction, and you say, okay, so now I get a quantum field theory in Schwarzschild with the Unruh state, or the Hartle-Hawking, whatever, you know. That will be the idea. So I think we should wrap it up. It's 11:50, and I was told that I should finish a bit early today. So, well, because there's a class here, and so to clear the room and so on. Okay, and I have nothing more to say, actually, so that's good.
Benito, what do you mean when you're saying you're not making reference to a Hilbert space?
Yeah.
With the equation you just wrote.
Which one? This?
Yeah.
Because I'm thinking of A, B, and so on as abstract algebra elements.
Okay.
Yeah.
Oh, as elements of a vector space.
As elements of a vector space with some product, right?
But the right hand side of the equation is making reference to the classical phase space.
The right hand, as I have written the right hand side, it would seem that I'm using some inner product, right? Well, it will, let's say like that.
I was saying that due to the omega.
Yeah, yeah. Typically the right hand side will, you see this is, yeah. Let me just, we'll see that in detail, but let me tell you something already. This is antisymmetric in A and B. And so on the right hand side you better have some antisymmetric stuff as well, right? And typically that antisymmetric stuff will be related to some symplectic structure or something like that. And we will it doesn't necessarily have to have A and B here. It could have some other little a and little b that are somehow related to A and B in some specified way. And I'll explain a little bit what, in particular, I'll explain for the Klein-Gordon field what the exact algebra that defines a Klein-Gordon is. And of course, it needs to have more than this. It should have a wave equation. So these elements better be related to some wave equation. There should be some reality condition if I want it to be a real Klein-Gordon field. So it should be self-adjoint. And it will be linear because it's a linear equation, and so on. So I've already spelled out some of the secrets for next time. But that's the idea. The idea will be to take an algebraic point of view to describe quantum field theory in curved spacetimes. Okay.
I want to make the point that I was making the last time at the end, once more.
Yeah.
It's regarding what you said earlier, on the left-hand side of the board.
Yes.
So you went from a notion of time to one that is accelerated with respect to the first one.
Yes.
Right? But you could go from one to another which are related by a boost, no acceleration. This is what we do all the time in standard quantum field theory, right? And there you can actually use all your machinery to actually show that these two theories would be unitarily equivalent.
Yes, of course.
So this pinpoints why all these effects do not show up in standard quantum field theory, right? You could actually explicitly show where the new stuff.
And the important bit is that you can do. It's very connected to this Bogoliubov transformation story. You will find that one theory can be represented in terms of the other one in a very simple way as a linear combination or something like that. And this entails that there exists a unitary transformation, right? And this unitary transformation is essentially a unitary representation of the Lorentz transformations that you have in space-time. Sure. Yeah, that is the whole point of flat space-time quantum field theory when, from the 20s and so on. Yeah. And this gadget really is, this other story that I'm telling really is about, take something that you cannot get to by applying one of these simple Lorentz transformations. Right. Okay. Okay. More questions? Okay. We're good? Okay. All right.